Hello friends, MoNaCo here. Lecture video 6 in physical behavior matter. We're talking about vapor pressure today. I personally call this boiling, but got to make things all technical and stuff. So vapor pressure is the focus here. We're going to define what vapor pressure is and be able to understand what the curves on table H mean. Okay, so that is our goal for this particular lecture. So we defined or redefined heat and temperature recently. Heat is the amount of energy that an object holds at a specific temperature, and temperature is the average kinetic energy of the particles that move. Now we're going to redefine boiling and what boiling is. Boiling point of any liquid is reached when there's a push me pull you between the liquid and the atmosphere pushing down on it. Atmosphere is always pushing down on us, so it's very hard for your brain to really wrap your mind around this because you don't feel the atmosphere pushing down on you when you're boiling water at the stove. Okay, so we're going to redefine that relating to vapor pressures and evaporation. Okay, so a liquid, obviously, it's a phase of matter characterized by its constituent particles appearing to vibrate about moving points. This is like a jar full of marbles mentally, if you're thinking about your particle diagram. Evaporation is the process by which surface particles of liquids escape into the vapor state. I remember that great image that I was drawn when I was studying this a long time ago. So you want to draw some particles in here. Make sure you're making this annotation. Okay, so these are all kind of liquid particles. They spread out to the walls of the container, but they don't fill the entire volume of the container up. Water evaporates, or particles evaporate, when these surface molecules kind of zip up and go off into the atmosphere. So the action by which the particles on the surface turn into gases is evaporation. So you can't evaporate from the bottom of a container. You can only evaporate from the top of the surface of the liquid. So it says surface particles. That's why it's important to note that. So we ask, can a liquid evaporate if its temperature is below its normal boiling point? Give an example. A normal boiling point is what it would normally boil at atmospheric pressure, 1.0 atm. Can we get something to boil below normal atmosphere? And the answer is yes, given the example of, well, there's a bell jar that we like to use. Or exactly like this. If you go up on top of a mountain, you will be boiling water. If you want to cook noodles in Colorado up on the top of the mountain when you're camping, you have to cook them for longer because the water boils at a lower temperature. So answer is like yes, if you're going boiling water when you're in a plane or at a higher elevation. At higher elevation, we also call this altitude. If you've ever noticed, if you've ever been on a plane, you ask for a cup of coffee, it's not quite as hot as you would have wanted it if you were down on the ground buying that from a Starbucks. Okay, because you can get liquids to boil at different pressures depending, and that's what the whole focus of this lesson here is. Vapor pressure, that's table H. It's the upward pressure exerted by a vapor in equilibrium with its liquid. So again, if we draw a picture here and we put the liquid particles in the bottom of our beaker, those arrows that I drew are the amount of pressure that these surface particles are exerting on the atmosphere. They're pushing, and the atmosphere itself is pushing back. And the only thing that keeps it as a liquid is that the atmosphere is winning. When the vapor pressure wins, the material boils. So what happens if the vapor pressure of a liquid is equal to the atmospheric pressure? The liquid will boil, will evaporate is really the best term to use. You could say boil, but it's really evaporating. Evaporation is boiling. So the phase of matter as a solid is where the particles appear to vibrate about fixed points. As the temperature of a liquid is lower, the forces of attraction between the particles become stronger. We call those IMFs. So as you drop the temperature of something, the IMFs take over and the atoms and particles stick together. Those attractive forces arrange them into an orderly fashion, kind of like the rows that we draw when we do our particle diagrams. We kind of make the solids kind of all clumped together in the bottom center of the container because those intermolecular forces take over. The motion of those particles becomes restricted. They only vibrate in place. They don't actually roll around the container. And the temperature at which a substance becomes a solid is its melting point or freezing point. And sometimes we call that the fusion point, where all the particles kind of fuse together. That's where the heat of fusion starts to play a role. All true solids have a structure called a crystal lattice. Okay, that's just some definitions around what a solid is, what it means to be a solid. What it means to boil, though, is about table H. And I want you to annotate this chart. 101.3 kPa. This equals 1.0 atmospheres, and this equals the normal boiling point. So if you're ever asked, what is the normal boiling point of one of these things, ethanoic acid, water, ethanol, or I think the other one up top here is propanone, you will have to look where their chart, their curve, crosses the normal boiling point line, representing 1 atmosphere of pressure. On the y-axis here, you have the vapor pressure, so how much that vapor is pushing up against the atmosphere. And on the x-axis, you have the temperature. So as you can see, let me fix that there. As you can see, as the temperature increases, the vapor pressure increases. So as you heat up the sample of liquid, the amount of pressure that it puts on the atmosphere increases. And water, this curve right here, has a normal boiling point of 100 degrees. Now we ask the question, can I get water to boil at a lower temperature? Sure it can. All I have to do is lower the pressure down to some less value, and the temperature that that water boils at will be, in fact, lower. I could get water to boil at room temperature if I wanted to, down here, about 25 degrees, because, oh, there we go. If I reduce the pressure almost to nothing, water is going to boil at room temperature according to this chart. So this chart's very simple to understand once you do some practice with it. Last thing we want to note here, the arrows that are pointing up, I've said it a few times, that is the vapor pressure. Those guys are fighting against the atmosphere, and the arrows that are pointing down are the atmosphere pressure. And boiling is a pressure game. So whichever pressure wins results in the substance staying a liquid or turning into a vapor. So if atmosphere is greater than the vapor pressure, we've got ourselves a liquid because it's pushing down harder. If the atmosphere is less than the vapor pressure, we've got ourselves some boiling occurring. Because the liquid is beating the atmospheric pressure, it's turning into a gas. All those atoms at the surface there are going, pew, see you later. I'm going to turn into from a liquid into a gas. The addition of energy there. So let's see what we got here. You should understand the basics here. Table H, how that normal boiling point is the dotted line there. And according to reading the curves, you can find the normal boiling point at certain various vapor pressures and certain various temperatures. So that chart is really just about reading the graph here. We got a lot of whole page and practice packet and POGL, as well as some online work for you. So thanks very much for your time. Thanks for watching.